I will come specifically to model order reduction and learning in the context of PDE, constraint optimization, and this is joint work that I did with several co-authors. I will come to particular contributions in my talk. So I will start with an outline. I will give you also some challenges for reduced basis approaches, in particular in context with PDE constraint optimization. And coming to this topic of PDE constraint optimization, I particularly want to introduce a completely different paradigm to look at model order reduction in such a scenario, which goes away from the classical construction of reduced models and then doing optimization with them. In this context, we then also go to time-dependent problems. We will see a combination of machine learning and reduced basis methods in the same flavor as it was already teased in the contribution of Gianluigi Rozza. And finally, we will also go to quite complex optimization problems where we directly go to machine learning to speed up computations. So let me go to the first application that we dealt with. This is a pore scale simulation of lithium-ion batteries. In these applications, you are really considered with resolving the pore scale geometry of the electrodes within a battery because you are interested in degradation processes. And one of the degradation processes that we looked at in this project, which was together with different industrial and academic partners, was so-called lithium plating. And lithium plating occurs when there are high currents at the surface of the electrodes, and the lithium ions then go to a metal phase, and this may cause even shortcuts within the battery, which might then even lead to explosions. So this is a phenomena that we wanted to study, and these local currents that are due to the singularities in the geometry are relevant for these processes, so you really need to resolve these complex geometries. So I will come back to this application in a minute. Another application, and you see that also this application has a lot of multi-scale structure, is the optimization and prediction of efficiency of catalytic filters. So catalytic filters, so this is a macro catalytic filter. If you look inside, you have the gas channels, and in between you have porous material where the catalytic reactions take place. And if you even zoom in to these catalytic filters here, then you see you have these microstructure simulations, and this is something that you want to understand and then scale up in this whole multi-scale process. But this is one application, and just to add another one, this is optimization in enhanced oil recovery. So you see that this is some oil field where you have typically induction wells and production wells. The induction wells, you pump water into your underground oil system, and this water drives somehow the oil towards the production wells where you produce the oil. In this project, we, for instance, want to optimize the control of these pumping devices for injection and production wells in order to get the most benefit out of such an oil recovery simulation. So I will come also to this application in the end. And as you will see in the end, these oil recovery, these are already quite complex nonlinear PDE systems that you need to solve. And of course, all the technology that you have with high performance computing is also needed for these kind of applications. And model order reduction and machine learning is always just on top of that. So there was a question in the chat. What about literature and books where you can enter this field? So again, I listed here several of these books that are now available. You saw two of them already in the presentation of Gianluigi, which is this book here from 2015. And this contribution here is this 3-volume contribution where you find lots of aspects of model order reduction. I also want to hint you, in addition to this book, which I also listed here with the cover page, where you find aspects of the theory of model order reduction and also aspects of algorithms and comparison of algorithms and their performance for different applications. So if it comes to model order reduction, we have, of course, always in mind that we do not only want to solve a large-scale PDE once. Because if you want to solve a large-scale PDE once, then you are more or less done with the full order methods that you all know, like finite element, finite volumes, and you should use methods like adaptive mesh refinement or HP refinement in order to get best performance for your particular query. Model order reduction is a technique that comes on top of full order model simulations if you are considered with more than just one solution of a PDE. And this can be also seen from this sketch on this title page of the book here. So what we are now considering are optimal design problems, optimal control, system simulation, uncertainty quantification, or real-time simulation. In each of these fields, whenever your problem is parameterized by a parameter mu, and you look for the PDE solution, and this PDE solution lives, let's say, in a continuous infinite dimensional space, or you can also think of your full order model, which lives in a 1 million degrees of freedom finite element space. Then for one parameter, your full order model gives you 1 point in this very high dimensional space. So if you now start to vary the parameter, then you follow a curve in this high dimensional space. If you have more than one parameter, then you follow a manifold, and the dimension of this manifold is bounded by the dimension of your parameter space. And here comes the active possibility to benefit from model order reduction techniques, because you see, if you have no a priori information about where to search for a solution in this infinite dimensional space, then you cannot build a very low dimensional approximation space that is indicated here by the red space Xn that has good approximation properties in all of this infinite dimensional space. But if you are after approximating such a curve in a high dimensional space, then this is just a one-dimensional object, or for a manifold, it's just a low-dimensional object. And therefore, you are now in the position that you can detect low-dimensional approximation spaces that have optimal approximation properties with respect to this particular class of solutions of your PDEs with this parameter variation. So this is an important point that you need to keep in mind. And it's not that model order reduction can, in all the situations, replace full order model simulations. So just as a first example, this is this lithium-ion battery project that I indicated before, where we are interested in this degradation phenomena. And if you apply the state-of-the-art reduced basis techniques, so you see this is the so what I have here is the underlying system of PDEs, which is a nonlinear parabolic elliptic system where you solve for the lithium ion concentration and an electric potential. And it's quite highly nonlinear coupled by the so-called Butler-Volmer kinetics that involve in the coupling of these equations exponential nonlinearities. So if you tackle these problems with the state-of-the-art reduced basis methods, then we can use the so-called POD greedy approach. So you use a greedy approach to select a parameter where you compute snapshots to compute the reduced space, and you use the proper orthogonal decomposition that was also announced by Gianluigi Rozza to compress the time trajectories and get only the most relevant information into your reduced models. So this was introduced together with Harstong in 2008, and there is also a priori analysis available from Werner Harstong. For the nonlinear treatment, we use empirical operator interpolation or discrete empirical interpolation, what was also announced. And we need a posteriori error estimates for the greedy procedure here. And as this is already a complicated system where we have no rigorous mathematical a posteriori error estimates available, we use a so-called hierarchical error estimation, which uses some heuristics. And this is an approach that we introduced in 2019. So let me just show you these results that you can have from such simulations. So in this particular simulation, we dealt with a finite volume approximation of this coupled system for batteries with about 1.7 million degrees of freedom. And if you do charging discharging sweep with classical full order models with this 1.7 million degrees of freedom, then it takes about 6.5 hour computing time. So this is typically you start your simulation in the morning, and shortly before you go home, the simulation is finished. If you apply this model order reduction technology, then you see here that you can bring down the computational time to 1.5 minutes. So this is what we obtained here, which means you have a speed up factor of about 280 with respect to the full order model simulation. So this is really something that is very nice, and there is also a theoretical theory available that shows why these reduced models are really capable to produce results with this quality, even though the reduced models in this case have only a dimension 30 or 40, which is really small systems. So in order to efficiently exploit that you do not recover your finite element or finite volume solvers, all this model order reduction can be put on top of the classical packages that are available for finite element or high performance computing. So for instance, in our case, the software that we provide is an open source development in Python called PyMore, developed by these authors. You find it on the web page here. And it has bindings, interfaces to your favorite package for full order model simulations. In particular, implemented interfaces are available for the Dune software, distributed unified numerical environment, for example, also to the Phoenix solver, the ngSolve solver, or the DL2 solver. And if your favorite package is not already implemented, then it's quite easy to implement bindings to your particular code that you are working with. So I now come to PDE constraint optimization, and this is clearly that we need to do something, because what I told you up to now is only half of the story. And therefore, I now want to go towards something that I call, we want to go beyond offline-online splitting. In the example that I presented before, we produced in an offline stage with huge HPC computations, a reduced model, which is then very fast to evaluate in the online phase. But the problem is that somehow this offline phase can be very computational demanding and also very storage demanding. I just want to make this idea clear for optimization problems by hinting you to this classical paradigm. So think of a PDE system that is parameterized here with two parameters, mu1 and mu2. So for every choice in this two-dimensional parameter space, I want to solve a PDE. And this is just a simple toy. You can also think of very high dimensional parameter space, and then this is a 10 or 100 dimensional or even 1,000 dimensional space. The classical paradigm of online-online splitting means that you want to construct a reduced model that has a guaranteed accuracy in all the parameter domains, so in all the box. But this might be very high offline computational cost and high storage, because you need really to take care that you cover the accuracy in all of this parameter space. If you want to solve instead PDE constraint optimization problem, then what you typically have is just solving the optimization problem with a full order model each step where you evaluate your forward problem, the PDE problem, takes a certain amount of time. So, and if you follow the full order model, then it converges with some rate. And what is plotted here is the error for the objective functional in such a PDE constraint optimization. If you use the reduced order model, then it might be the case that the offline time that you need to construct your model is already larger than the time that you need to solve your PDE constraint optimization just using a classical full order finite element model. So this is typically the situation that you can encounter. Of course, if you do not count this offline time, if you are not interested in this overall computational cost and you only take care how fast is your online optimization process, then this is instantly, because the computational forward problem with the ROM is so fast that you are directly solving these optimization problems. So it depends always on your goal, whether it really pays off to go for reduced order models, or whether it's already from the beginning better to just stay with the finite element computations. What I now want to show you is a new paradigm. And this new paradigm is online enrichment, or as I also call it, learning on the fly. So we want to learn a reduced model not by just in an offline phase preparing the model and using it in online phase, but we want to learn it while the outer optimization loop is running. So if your optimization loop is running, then you start with an initial guess of your parameter, and then in each step of the outer optimization loop, you get a new parameter until your optimization loop has converged. So you see in the solution process of an optimization problem, it's not even that you need a good solution of your reduced model in the whole parameter space, but actually what you need is just you need to get information from your system to find a path towards the optimal parameter, and there at the optimal parameter you need to have a defined accuracy to solve the overall optimization problem. So the change in paradigm is now we do not aim at reduced models that are capable to give accurate results in all parameter domain, but we just focus on the solution of optimization problems, and we want to construct reduced models or learn models that are able to guide us to the solution of the optimization problem. So that's what we are now going to do, and we want to put this into a rigorous mathematical framework. So this framework is the so-called reduced basis trust region approach. So in order to formulate this, I now introduce some notation. So for now, we consider an objective functional that we want to minimize, and this depends on a parameter and a state, and this state, this is the PDE constraint case, is subject to a variational problem, which might be an elliptic or also time-dependent PDE that you can formulate in such a variational form. Of course, if you want to solve this optimization problem, then what you need is typically a gradient descent type method for solving for computing this minima, and such methods usually use evaluations of the objective functional, of the gradient of the objective functional, or if you go towards a Newton method, even Hessian information of the objective functional. And the target is, of course, in order to compute these values of the objective functional, you need a lot of forward solutions of the underlying PDE, which makes this task so computational expensive. Even more expensive if you go to real large-scale or multi-scale problems, where already one of the solves with classical full-order models is already a challenge. So there is a lot of literature that deals with reduced order models for PDE constraint optimization, starting with the first work maybe of Ohlberger and Patterer in 2009. And the more recent works, they follow more the direction that I presented to you with online enrichment and on-the-fly learning of reduced models. So again, we start from these optimization problems, and what is the idea of using these trust region approaches. So how can we find the way from a starting parameter to the solution of the optimization problem by minimal computational cost. So how can we find a way to go from an initial parameter guess to the optimal solution? And one answer how you can do this is the so-called trust region optimization method. In this trust region method, you replace the overall optimization problems by a sequence of local optimization problems that you only solve within a so-called trust region. So you replace the minimization problem of your original objective function by the minimization of a so-called model function mk in each iteration step k. This model function, in our case later, will be given by a sequence of more and more accurate reduced models. So the solution then of this local optimization problem then updates your global optimization loop to the next parameter. So you go from mu1 to mu2, and you solve the optimization problem only in a region where you trust your model. And this in the trust region approach is given by this constraint that the update needs to be bounded by some radius delta k. And I show you now how this paradigm of trust region can be transformed to an error-aware trust region. So the error-aware trust region replaces that you solve the local problems in such an area of radius delta by solving this local problem in a region where actually the relative error of your problem is smaller than a given tolerance. So what you see here is an a posteriori error estimate of the error in your objective function divided by the absolute value of the objective function is the relative error in the objective function. So you should be able to compute this error. And of course, this should be efficient. So you need efficient a posteriori error estimate of this quantity. If this is available, then you can judge for a given initial point, mu0, what is the region where you trust your method. So this region where you trust your method can now have arbitrary shape. And it only says that within a certain region around this parameter point, I can trust my model up to a given prescribed tolerance. I can do the solution of this inner optimization problem, and this is the black line that you find here, until I reach the boundary of this region where I trust my method. And at that boundary, I need to enrich my reduced model. I need to improve my model function such that I also get a guaranteed valid model in the next steps where I continue my optimization loop from here. So in the next step, this trust region might look like this darker blue region here. And you see as the model collects information that you created during the outer iteration, this trust region will always contain the way that you walked through your parameter space until at some point you find the optimal solution. So this is the paradigm which was first introduced in this paper of Gern Kreppel, Roy Wilcox, also with some theory. I want to go now into the details of a posteriori error estimation and getting the contributions that we need in order to write down this algorithm here. And as you will see, this will be a non-conforming dual approach. And in order to have an idea what's happening here, you need to write down the first order optimality system for this kind of optimization problems. And then you notice that this first order optimality system consists of a primal state equation, which is the underlying variational PDE constraint. You have, in addition, the dual state equation. So this is an additional PDE for a dual state P mu, where the right-hand side depends on the primal state U mu. The dual state and the primal state, and this comes from this optimality condition, they can be used in order to compute gradient information of the objective function as indicated here. So we want to have a reduced gradient. And this reduced gradient is given by the parameter derivative of the Lagrangian of the optimization problem that is evaluated in the primal state and the dual state. So computing primal and dual state and looking at this quantity, you get derivative information of your objective function in each direction of the parameter state. If you go to even higher order methods, then you might not only need primal state equations, but also sensitivities of primal state and sensitivities of dual states, where sensitivities always mean derivatives with respect to the parameter of the primal solution or of the dual solution. These are the sensitivities. So what we need now is implementation of all these equations, and we need actually for our algorithms also a posteriori error estimates efficiently computable for reduced order models for all these equations. And this is something that you can actually do, but there is one thing that you need to take into account. I told you that you need to look at the Lagrangian where you plug in the primal and dual solution, and you do this now for the solution of the reduced order model, UN and PN, which are computed by the typical projection of these equations into the low dimensional space. If you write down this objective, this Lagrangian here, you need to take into account that you might have the situation that the solution space of the primal solution and the dual solution is not the same. And this is the target in our optimization method here, because you want to tailor the reduced spaces, particular towards the primal and dual equations. And this leads to the fact that you need to not only consider the objective function where you plug in your reduced model, but you need to take into account also the primal residual where you plug in the primal and dual solution. And if primal and dual solutions would live in the same space, then the dual solution would be a valid test space for the primal problem, and this residual would be zero. It would not be there. So in our case, the method is non-conforming in the sense that this residual here is not zero, and you need to take into account this in your error analysis. So if you do that, then you have the possibility to derive rigorous full a posteriori error control for all these quantities. So the error in the primal solution between reduced model and full order model, in the dual solution, in the objective function, in the gradient of the objective function, and also in the sensitivities. And all this is rigorous and is there. I just want to focus now on this a posteriori error estimate for the objective functional. So what you can show then is that in our approach, this error here can be expressed with the a posteriori error estimate of the primal problem with an evaluation of the residual of the dual plus a term where the primal error estimate appears in a square. So you see that the objective function converges quadratically, let's say, with respect to the error that you expect from the primal solution. And you can do the same kind of a posteriori error estimates also for the gradient of the objective function, and you get an explicit, fast to evaluate estimate for that. So if you have these estimates at hand, we can now formulate our overall trust region reduced basis methods, where we have as local minimization problems where we replace the full order model by the reduced order model that we have in this situation. And the trust region, the error awareness is represented by this relative error bounded by a fixed tolerance here. And this can be computed with our fast a posteriori error estimates. For this method, it's not only a fast algorithm and we have good results, but we have also full theory for the convergence of the optimization solver. So we can show that every accumulation point that you might have is actually then a critical point of your objective function. So it's only local convergence. You cannot ensure with this global convergence of your method. And this means that in the end, for this box constraint optimization problems, this is the condition that a point mu bar is actually a first order critical point. So this is full theory available. And I now show you some numerical results. So what we do here is we want to optimize heating and also the building in a typical house. So for instance, here you have a ground floor of the building where I'm currently in. And in this building, we have a childcare room where we want to have a defined temperature. And the optimization problem is done in such a way that you want to minimize heating costs, and you have heaters that you can put on, and you have also different material in the walls, in the doors, in the windows that can be varied. So if you look at these problems, then you see this is the heat conductivity for these kind of problems. This is one of the possible forward solves. This is one heater on, so this is the source term, and it can be up to 30 heaters on here. And this is a dual solution that corresponds to this situation. So this is, of course, the full order simulation, and then we optimize and we compare now the overall CPU time for these optimization problems between an optimization algorithm that directly works with the finite element full order model. This is this red curve here. So this goes down with a certain speed for this method, and we compare with the trust region reduced model approach that I showed you before, where you see there is no offline time. So there is no time that we use to create in an offline phase a reduced model, but we train and learn the reduced model during the first steps in the optimization loop, and therefore the curve here, the error versus real CPU time, follows more or less the curve of the full order model. And you see that at some point, I learned a reduced model that is good enough, and then I get the full performance of the reduced order model, and I converge very quickly with this optimization problem. And you see that I can now compare the CPU time of everything together without neglecting offline computations that are probably very expensive, and I get very good speed ups. So this is the philosophy, and I now want to come towards time-dependent problems and what we can do in order to speed up not only in space with the reduced basis method, but also in time. So we now look at, let's say, parabolic problems, where again, A is just an elliptic or coercive bilinear form. And we are in this many query scenario where we have a lot of evaluations for varying parameters. And we will also come back to using this in an optimal control or PDE constraint optimization process. So the obstacle is that I reduce with the reduced order models, I reduce the system in space, but due to stability reasons, I need to do a time integration of the reduced model with the same number of time steps as the original model. And if you have something like 10,000 or 100,000 time steps to solve, this is really an obstacle, because you want to reduce this large amount of time steps as well. And this is done now by combining model order reduction with machine learning with an idea that was already also presented by Gianluigi Rozza. So if we have our reduced solution, then we can write this down as a span, that the solution is a span of a given basis function. So these are now the reduced bases where I span my reduced space with. And the solution is then defined by giving the time-dependent coefficients with respect to this reduced basis. So this is something that we want to compute, and the classical way is to do Galerki projection methods and time iteration of a reduced system in order to get these coefficients. And what we do now is we do not compute these coefficients by these classical projection methods, but we now learn directly a map from the parameter to the coefficients in this expansion. And this can be done in two different ways. It's what we call time vectorized or random access. So one way is that we actually train a machine learning model that maps from the parameter to this coefficient vector. So for one parameter, you get the coefficients of the whole time trajectory at once. And the other one is you learn a map that maps from parameter and time to the corresponding coefficient in parameter and time. this gives you random access. So if you have trained such a model, then you can evaluate the solution at any time without doing time iteration. If you have trained, let's say, a deep neural network or other machine learning models that gives you an accurate result on these maps, then of course you can just use these coefficients, which we now call machine learning coefficients, and you can plug this in this expansion here, and this gives you a machine learning answer to these state equations. So what do we have here? We have a hierarchy of models. We have a full order model, arbitrary accuracy, but very slow. We have a reduced order model, which is much faster than the full order model. We have error estimation here. And the cons are the time iterations take long time. And this is where machine learning can help. We get a parallel and fast evaluation in time. The con so far is that these rigorousness of having a certified model with error estimators gets lost at the first sight if you use the machine learning. So there is no certification, and this is actually where you can now benefit if you combine these approaches. Because we have a posteriori error estimates available for the reduced basis methods. In this case, such an a posteriori error estimate for the difference between the reduced basis solution and the full order finite element solution is given, for instance, by a sum on these dual norms of the residuals in the time points tk. And in order to evaluate this a posteriori error estimate, you only need to be able to evaluate the residual where you plug in your reduced approximation. And if you now keep in mind that the reduced basis approximation lives in the same space as your machine learning approximation, then it's completely clear that this a posteriori error estimate can immediately also be used in order to certify the machine learning prediction, because you just need to replace the reduced basis solution by the reconstructed machine learning solution here, and you get a rigorous certification also for this combination with the machine learning model. And this is what we use now in a kind of black box simulation method, where the idea is behind this black box, you have a model that gives for a parameter that you put into this system a correct answer with a given tolerance. And you do, as a user, you might not even care what is going on in this black box. But this black box has a hierarchy of models. It has a full order model, it has a reduced order model, and a machine learning model. So if a new query for a solution for parameter mu is asked for, I first ask, is my machine learning model inside my black box good enough to give accurate results? If this is the case, then you just return the solution of your machine learning model. And here you need the a posteriori error estimate in order to answer this question, whether this is accurate enough. If this is not the case, I need to fall back to my reduced basis method. This then generates a whole time trajectory of reduced solutions. And this again can, once used to give a result, so this is the result of the PDE, but it at the same time collects training data, and this collection of training data that is done here can be used to improve your machine learning model for the next iterations. And in the same way, if your reduced basis method fails, then you need to fall back to a full order model calculation. And this again collects training data, snapshots that you might feed into an improvement of your reduced basis model, and again this feeds into the machine learning model, which gets improved. So this is the strategy that we follow, and we apply this to a benchmark problem for such a reactive transport where you have this pollutant in a flow channel, and you have a watch code with a reaction, and you want to somehow optimize the catalytic reaction here. So if you do that, then the optimization problem, what you want to optimize, in this case has two parameters. We can vary Peclet number and the Damm-Köhler number of this physical underlying physics. And we want to find the minimum of the objective function, which is here given in color. And you see that the optimum is somewhere here. We start at some point, and then the optimization solver will start. They use a lot of forward iterations in these different parameters in order to come towards the solution. And the most interesting figure here is this figure here below. This shows you that this black box is called in order to solve this optimization problem. And what you see here in these different colors is how often in this loop the full order model is actually needed and called, how often the reduced basis method gives an accurate result, and how often everything can be replaced by just using the machine learning model, which is really fast. So you see in the logarithmic scale here, the CPU time, which means that you have a huge CPU time if you need to call the full order model and solve the full underlying system. The reduced order model is already much faster, and the machine learning model is even faster. And you see it's a logarithmic scale. And this means in order to solve this optimization problem, all in all, you need only 1, 2, 3, 4 full order model solves, and everything else can be handled by the reduced basis and machine learning model, which gives you a real speed up of this technology. Last but not least, and I think I have a few minutes left, I want to go towards the last application problem where actually the underlying PDE is so nasty that the reduced order models are really, really difficult to realize. So we come now to a purely machine learning driven speed up of PDE constraint optimization in the context of this enhanced oil recovery. And I remind you, what we want to maximize is our so-called net product value, which is the amount of US dollars that you get out of the exploitation of your oil field. And the parameters that you have are somehow the injection rates here and the production rates here, and they contribute to the overall cost functional. In this cost functional, J, you have components here with a plus sign. So this is something where you gain money. This is, for instance, the oil that you pump out of these production wells. And then you have some parts with a minus sign here, and this collects all the costs. And these costs are with respect to the pumping rates in the injection well, with respect to the polymer that you pump into this field in order to get in this so-called black oil model, the optimal production of oil. So this is the objective functional. U is now the value that you want to optimize on. So this is the pumping rates. The control is U, and theta is additionally the uncertainty in the problem, because you have these configurations of the subsoil not in a deterministic way, but just in a stochastic way. Such that for each stochastic realization, you actually need to solve such optimization problems, or you do an ensemble optimization where you want to take into account the whole ensemble evaluation with respect to this uncertainty. The underlying PDE system that depends on the control is the so-called black oil model, where you have 3 phases: a water phase, an oil phase, a gas phase, and in this example, 4 components, which is water, oil, gas, and the polymer. And you see that this is a really nasty parabolic degenerate problem with strong nonlinearities, as you know, from multi-phase flow in porous media. And therefore, we decided in this case not to go for a reduced order model that needs to project this really nasty nonlinear coupled system into a reduced model with all the techniques of empirical interpolation. But we directly went to an approach where we speed up the overall optimization process in a way that you want to get a surrogate model for the evaluation of the cost function. So what you do here is either you want to construct a machine learning model, so a deep neural network, for instance, to approximate a mapping where the control rates are directly mapped to the value of the overall objective functional, or a little bit more sophisticated is this vector valued case, where you use the structure of your objective functional because you can write it as a scalar product of a vector of weights times a vector of contributions that are added with these weights to give the overall objective functional. In this approach with the vector valued case, we now map the controls that live in this space to this vector of components of the objective functional that is then multiplied with these weights to get the overall objective functional. So how can we benefit from these machine learning models in the overall optimization loops? And also here is the same story as I told you before. We do not need a machine learning model that has really good predictive quality in all the parameter or control domain, but we just need it on the path to find the actual control of the system. So what you see here is again indicated a path of an optimization solver, where here you use just a gradient descent method. You start with some control parameters and then you do your optimization until you find an optimal control. In these examples here, we do not use primal dual equations in order to compute gradient information, but we use an ensemble optimization algorithm, which means that in each point here, we actually throw randomly in this area 40 parameter points where we do a solution of our full nonlinear system. And from these ensemble of solutions, we compute gradient or even Hessian information. So whenever you see one point here, it means like 40 times solving this complex nonlinear black oil model, computing a gradient, doing a gradient step. So what we do instead is when we compute these 40 points here in order to get gradient information, we use these 40 computations here already to train our machine learning model. And then instead of directly using just going to the next point where we again need to do a lot of full order model solves, we do this optimization problem by using this surrogate model, which is now a pure machine learning model. And we do an optimization loop, which is very fast until we come to a new point where the machine learning model is already minimized. Then again, we do with the full order model a gradient evaluation. We get a new enriched machine learning model, and we can go on and we find in a very few macro steps the way towards the optimal solution. And these ways in between can be done with just using the machine learning model. So if you do that, then we get the final results. And what you see here is the solution of this optimization problem. So this is now in US dollar what you can exploit in the oil field. And you see that the same algorithm that is only based on the full order model source has a lot of iterations. And actually, it also converges to a different local minima than when you use this machine learning combined approach, where you have very fast convergence. And in these cases, we converge towards optima that are even better than those that you find with the full order model. So the machine learning model, that's the way, as we look at it, this introduces some regularization to these very nasty optimization problems that guides you in these two computations here to better local minima of your energy or your functional landscape. It's not only that you get better results and much faster computations. If you look into the controls, then you see that you also get really different controls. So this is the production of oil, and you see that with the two machine learning models, you get a higher oil production rate than with the full order model. But the two approaches with the scalar and vector valued machine learning model, they give different reasons how the overall outcome or performance of the black oil exploitation is done. So one of these models finds a minima where the oil production is maximized, but at the same time, it has higher pumping rates for the water, which means this is a higher cost. And it has also higher polymer production, which is a higher cost. The other model produces less oil, but also has less cost in the production of water and oil. So that's how you can compare these examples. And the overall results are in this solution process of the really complex optimization problems. You get a speed up of about 13 or 12 by using this machine learning approach. So even more challenging problems, but there is no time today, are parameter optimization problems where the underlying PDEs are multiscale problems. And this is something that might be quite of interest for you if it goes towards exascale computing, because then you can consider a domain decomposition technique where the grid that I show you here is just the macro domain decomposition of the underlying problem. And you can think of this new approach here as an approach where in each of this macro domain, you produce a reduced order model for this local part of the overall computational domain. And this leads to a so-called localized, so this takes the multiscale methods into account, localized regional reduced basis approach. And you see in the color here, this is the number of base functions locally in this particular examples, which then takes into account that the complexity in some part of the domain is much higher than in other parts of the domain. And even more challenging is if you do not only deal with parameter identification with a limited number of parameters, but for instance, with inverse parameter identification, where the parameter field is something like a diffusion field, and this is infinite dimensional or very high dimensional parameter space. So in these cases, the traditional reduced basis methods, they all fail from the beginning because of this high dimensionality of parameter space. And just recently, yesterday, we published a paper on that where you can find the ideas of a combined state and parameter space reduction. So in this context, we exploit that we can also devise not only a method to reduce the approximation space for the state, but we can also reduce the approximation space for the parameter, because in the end, in this infinite dimensional space, you want to find just one point. And this gives you also the possibility to do a very, very efficient reduction here. So with this, I'm at the end of my talk. I thank all my collaborators that worked on these kind of problems, and I'm open for questions.
Thank you very much. I must say your and Professor Otza's talk was aligned in many aspects. Yeah.
Right.
Yeah. Thank you very much. Yeah. Yeah. So time for questions. So I have a question for you, because you mentioned initially in the lithium ion case that there was a singularity, some sort of.
Yeah. So you know that. So I come back to this picture.
Yeah.
Oh,
very first slide, maybe.
Yeah. So you know, if you solve an elliptic PDE and you have entering corners, then you have singularities.
Yes.
And if you look at this problem here, this is a coupled problem between the lithium-ion transport and an electric field. And this electric field also, because of the re-entering corners in the geometry here, show very high electric currents in certain localized region. And if you replace these detailed simulations in the full geometry just by a homogenized model, then you can never resolve these fine peaks in the local currents. This is the reason why in these examples here, we really need to resolve these complex geometries and really solve the PDEs in this poor scale system.
Okay, so was that was that an issue during the machine learning model that you had to map this singularity also from the input parameter space to the solution field? Yeah.
No,
Was
these
it any
kind
special
of singularities here are actually not a problem for the reduced order models or machine learning. So they can deal with it. This was just a reasoning why for such applications you really have to resolve the detailed geometry, and you cannot go with a homogenization approach. So homogenizing these equations. So this is the typical approach for the so-called Newman models, where you have just an averaged equation for the simulation of batteries.
Oh, okay. Yeah. Thank you. And my second question was also about that rigorous error estimate. So you had error estimates for the machine learning model, which is something new. So yeah, because normally there is a problem with machine learning models that to trust that there are no error estimates or some theoretical proofs.
This is actually new, and the point is that if you just use machine learning without this combination, so you see that in our case, we just use the machine learning to compute the coefficients in this basis expansion. And this means with this expansion, we first compute with machine learning the coefficients, and then we can reconstruct a full solution. And this full solution can be plugged into the residual, and then we have the error estimate. So this is the crucial step here, that we use this combination of a reduced order model with a basis that allows the reconstruction together with machine learning. Only in this combination we get the certification.
Okay.
But this is actually the new contribution in this article. Yes.
Yeah. So yeah, this is also important. And one more thing that you mentioned the hierarchical error estimation for hierarchical error estimation during your initial slide. So
Yes.
was that also like was that also part of this error estimate for the machine learning models, or no? They are completely separate frameworks.
So these are separate frameworks, but you can, if you want to use this in the machine learning context. I gave you this error estimate, and this is a rigorous error estimate for the simple parabolic equations. If you come to more complex problems, then such rigorous error estimates are not available. And this hierarchical error estimate that we suggest, they can be used to replace this estimate here. And the idea behind these hierarchical estimates is that we know a priori that for large classes of PDEs, the error of these reduced basis methods, they decay exponentially with the number of basis functions. So this is a comparison of the error estimate for a greedy method with the so-called Kolmogorov n-widths. And from this result, we know that if we take a reduced model and compare it with a reduced model with a larger basis, then we can expect that the error between these two is a good approximation of the error with respect to the really full order model solution. And this is behind the hierarchical estimate. Okay, and for this, there is some heuristic. So you need to have a satisfied saturation criteria that you are already with the reduced method in the region where the method decays exponentially with respect to the number of basis functions. And if this assumption is met, then this is also rigorous and gives you a good estimation of the error. And in addition, with respect to the classical a posteriori error estimation, it does not overestimate the error in the same way. So you see, you have this inverse of the causative constants, or in an im-sub-stable problem, you would have the inverse of the im-sub constant, which you usually need to estimate or to get an upper bound for. And this leads to a large overestimation of the error. And this overestimation is not there for these hierarchical estimates.
Yeah. Thank you. Yeah. And of course, you already answered the book on PDEs, or the reduced order model for PDEs in your slide. So yeah.
Yeah, I can get back to that also. Yeah. So this is really that meanwhile there are really nice books that you can also give to students to get an introduction into that. So the first two books here, Quattarona Manzoni Negri and Hesthaven Rotzer Stamm, they appeared more or less in parallel. They are both concentrated on the reduced basis method. So they both reflect the reduced basis method. The book that I present you here reflects a much larger class of model reduction techniques. It's not only on reduced basis, it's also on system theoretic approaches like the balanced truncation, which is another model order reduction approach. And it also includes data-driven approaches and also gives them a comparison between these different approaches.
Yeah, this of course there are more questions, but yeah, we will restrict here, and yeah, we will go to a break, and we will return within 15 minutes for our next talk. We would once again like to thank you, Professor Ohlberger, for his time. Yeah,
Welcome.
and thank you very much for your interesting talk.